Let's discuss a few examples of Lipschitz continuous functions, and then discuss a few of their properties. So for instance, we can look at the function sine of x. Is this Lipschitz continuous or not? Okay, so actually this is a differentiable function. Okay, because it's differentiable, I can take f of x1 minus f of x2. Okay, I know it will be equal to f prime of c times x1 minus x2 by the mean value theorem. I can do this because the function is differentiable. But then f prime of x is the cosine of x. How? So we are almost set here. If I write down the absolute value of the difference of the images by f, okay, this is the absolute value of f prime of c times x1 minus x2. And this is the absolute value of the cosine of some number c, okay? This is for some c in x1, x2. Doesn't matter. And why doesn't it matter? Because the cosine is less or equal than 1, regardless of what particular c I'm talking about. How? So actually, f equal the sine of x is Lipschitz continuous with constant 1. Okay, and actually this we did, it's a more general fact. I'm sure if I write now, let's say square root of x squared plus 1, it's clear that the same trick is going to work. Okay. Also, Lipschitz continues with k equal 1. Okay, as long as it's differentiable and the derivative is uniformly bounded, we are good to go. Let's do the computation nevertheless. The first part, I just do a copy paste. Okay, and then I just take absolute values. And I need to compute the derivative. X squared plus 1 times 2x. So this is x divided by square root of x squared plus 1. So f prime of x in absolute value. There we go, now it's going to work. X squared plus 1 less or equal than absolute value of x over x squared, which is equal to 1. Okay, so again, Lipschitz continues with constant 1. One example of function that is not Lipschitz continuous would be if I take the square root of x. Okay, here the problem is that the square root of x at 0 has infinite slope. Okay, so as I approach 0, at some point, doesn't matter how steep I pick the slope of the cones. Okay, they will be okay for some time, you see, but as I approach, there is a problem. Eventually the function escapes. Okay. And that is because the derivative is not bounded. So here, this is not globally Lipschitz continuous. Okay, let's say in 0, 1. Okay, to keep things simple. Now, what's the problem here? By the way, I say not globally Lipschitz continue because it is locally. Okay, how do I figure this out? So if I look at the derivative, now, yeah, I'm dividing by the square root of x. So this goes to infinity as x tends to 0. Okay, but f prime of x is bounded above and below for any compact, let's call it U, contained in 0, 1. Okay, so what I'm saying here, this is by the extreme value theorem. Okay, the function is continuous inside 0, 1. So if I take any interval there, I will be able to find the largest slope. Okay, so that is the reason why it's locally Lipschitz continuous. And just one final comment. This one is actually an example of Helder continuous. With exponent less or equal than 1/2. Okay. In general, if I take x to the power alpha, alpha less than 1, like this, then it's going to look like a bird. There we go. Okay, this is the prototype of Helder continuous. With the exponent alpha. Okay, and actually the Helder continuity graphically means that we can place one of these birdies from above and below and move it along the graph of the function f.